A 20-foot ladder leaning against a wall begins to slide. When the base of the ladder is 12 feet from the wall and moving at 5 feet per second, what is the change in angle of the ladder with respect to time? Okay. So, what is the angle theta with respect to time? So we're looking for d theta dt. We're not really given an equation here, so we kind of have to make one. So whenever we see triangles, we think trigonometric equations, and so we're going to think SOHCAHTOA. For this one, we're going to use sine. If you choose the wrong one, that's okay. You'll realize halfway through, and then you have to go back and fix it. But it won't be like disastrous, unless you're very short on time, in which case it may be. So for here, we'll say that sine of theta equals opposite over hypotenuse, which equals x over 20. Now I know this is 12 here, but I'm going to call this x because this is going to change with respect to time. As the ladder is falling, that's going to get bigger until eventually, the ladder is completely fallen and that x would be 20. So now we have this equation, this side and this side. We're going to take the derivative with respect to time. You might be thinking, wait a sec, why do we do time, not x or theta? That's a good question. What we're looking for is the change in theta with respect to time. You might be able to find everything with respect to x as well, but that's not what we're being asked for, so that's not what we're really going to pursue at this point. So we're going to first try to find everything with respect to time. So taking the derivative of sine of theta with respect to time, we get cosine of theta, and then we do the chain rule, d theta dt, equals derivative of x with respect to time would be 1 over 20, because derivative of x with respect to time will be 1, times the derivative of x with respect to time. And we can think of that in terms as the chain rule. And then from here, we'll plug in the data that we know. So let's change over to purple. So we have d theta dt equals 1 over 20 times dx dt times 1 over cosine of theta. Okay. So we want to find out what the cosine of theta is at this point. And we'll go back to SOHCAHTOA. So cosine of theta equals adjacent over hypotenuse. So this will be 1 over 20 times dx dt times, it's normally adjacent over hypotenuse, but this case will be adjacent over hypotenuse because it's 1 over cosine theta. And then we will look at this and figure out what adjacent to hypotenuse is. We know hypotenuse is 20. I guess r would probably be more correct. And then adjacent, which would be this part right here, would be 20 squared minus x squared square rooted. No. Maybe. So it'll be x squared plus y squared equals 20 squared. So then y equals 20 squared minus x squared square rooted. Yep, I was correct. Go team. From here, we'll plug in our values and we'll just kind of, see what happens. So I'm going to move this 20 over there. So we have 20 over 20 dx dt times 1. And now we have the adjacent, which is 20 squared. And we know x at this point will be 12 minus 12 squared square rooted. Don't think I'll try to do this one in my head. Nope, not going to try and do it in my head. So dx dt we also know to be 5 So this is where I'm going to do Wolfram. So it's 400 minus 144 square rooted. Yep, I'm going to go to Wolfram. So we have 5 times, and you could do this on a calculator. It's not that difficult. So we have 400 minus 144. Do another bracket here maybe. Square root, maybe another parentheses. Yeah, you can have a third parentheses. That's probably good too. And our answer is 0.3125 equals 0.3125. And this will be in radians per second. 0.3125. Yep, even possible answer, which is nice. So to backtrack, this was fairly cumbersome. So we're asked about, all right, we have this ladder of a known length, and it's falling down a wall. We're given at a specific distance from the wall for the base of the ladder, we're given that how fast it's moving away from the wall. So we find a formula to work with, an expression, an equation. Actually, equations and expressions are different, but that's fine. We're going to go with this. Using sine of theta equals x over 20. And that gave us an equation that we could work with to find the height of the ladder. We took the derivative of that, and that told us the change of one of the sides, in this case the base, with respect to time. It also gave us the change of theta with respect to time. We worked with that, we ended up with a cosine theta. We then converted that cosine theta into adjacent over hypotenuse using SOHCAHTOA. Fiddled around a little bit, put it in our calculator, and got an answer that seemed pretty much reasonable. And it turns out it was both reasonable and correct. So that gave us then the fall, how quickly the angle was changing at that specific time that was given to us. You might be like, wow, how did you know how to do all this? I didn't. The secret to a lot of these problems is you really don't know where to start, but it's kind of like, okay, I can kind of see what to do something with this. And the idea is doing something is better than doing nothing. So you just start walking through the woods, and hopefully you get to grandmother's house or reach the end of the woods or something good happens. But you're right, you are kind of stuck in the dark. You just got to take some action. And hopefully it turns out well. And I know it's kind of depressing, but alas, that is the plight you deal with when you're doing story problems. Hope this helped. Thank you much. Go team.